Thank you very much for the invitation, and it's my great pleasure to be here. So today I'm going to talk about a recent topic that I'm working on. So it's called latent graph discovery. Here I will talk about three works. So the latent graph for labels, the latent graph for time series, and the latent graph for concepts. So this is the outline. So first I will talk about the general story of latent graph discovery, the motivation, and the past work. And also, the first work is about the latent graph among time series variables. And the second work is a quite old work. It's about the label correlation. And the third work is about a recent work. It's even ongoing and not yet published. It's about the concept graph. So, I suppose most of the people here are working on graph neural networks. So you know, if you want to use graph neural networks, first you need to have some graph structure. But in many cases, actually you don't have a graph. For example, if you have an image and you want to predict some labels, so actually some labels may have correlations. For example, if you have a label as beach, generally the beach will just be correlated with sand and ocean. So if you search beach in Google image search, you will find a lot of such images with both beach and ocean, and maybe sand, and sometimes also sand. So you will see there are some correlations between the different labels. So sometimes you can get this kind of correlation graph from knowledge graphs, but that's not always the case. So sometimes, actually in most cases, you don't have the graph to connect the different labels. So if you just predict the label independently, then maybe you will lose a lot of information, and that's not so accurate. So you have to consider the correlation in some way. And also, time series, that's another domain which you may want to use latent graph. For example, in the medical time series, if you have some time series data for the patient history, you may have the lab test values like heart rate, temperature, and blood pressure. So all these kinds of variables, actually they are correlated. So you have to consider the correlation between different variables in your time series data, and this kind of correlation can also construct some latent graph. And also in the financial domain, if you want to predict the future stock price, actually different stocks will also have some correlation. So you also need to consider latent graph among the stocks. And also in the traffic network, sometimes you only have the node information, but you don't have the underlying network to connect the different nodes. So that's also a latent graph. In other domains, like if you want to get some gene regulatory network, generally it's also inferred from just some gene expression data. You actually don't have this gene-gene interaction network. And also in the computer vision, sometimes you want to infer the same graphs. So you only have the objects, but you want to predict the relationships between different objects. So that's also a latent graph. Okay, so latent graph discovery is also called graph structured learning in many cases. So early research focused on the graph learning from Bayesian network perspectives and also the graph signal processing perspectives. So these are two papers which summarize different domains very well. So for the Bayesian networks, generally they call it structural inference. So it's constraint-based or score-based. Score-based means maybe you can just calculate the log likelihood of different graphs, and then you can say, okay, which graph give you like a better score, and then you can just select that graph as your, latent graph. Graph signal processing is more like an optimization-based method, so you can consider the smoothness of your signal, so you can construct some optimization-based methods to learn your latent graph. For example, you can just learn the precision matrix. Recently, so there are more and more graph network-based methods to learn the latent graph. So one famous work is called neural relational inference. And we also have LDS, learning discrete structure, and DGM is kind of a unified mechanism for graph structure learning. And also SLabs is self-supervised learning for graph structure learning. And we also have some benchmark data. So we have the OpenGSL and GSLB, which were published almost at the same time. So this is a typical pipeline, which is summarized by DGM. Generally, we are giving some node features with the initial graph or without the initial graph. So the initial graph structure is just optional. And based on the initial node features or the initial graph, you can just update your initial graph. So you can learn the latent graph based on the node features or the initial graph together. And then once you have the latent graph, then you can do the diffusing of the graph neural network to update your node embedding, and then you can just iteratively learn the next step. So that's the pipeline of the DGM. So in the differentiable graph module, actually you can do two kinds of sampling to learn the graph. You can do continuous sampling or you can do discrete sampling. So continuous sampling means you just assume the probability as as the weights of your edges. So you don't need to do any sampling. It's just a continuous graph. And discrete graph sampling means you have some probability based on the similarity or something, and then because it's just a probability, you cannot directly use it. So you have to sample the discrete links between different nodes according to your probability. So it's just like a binary links. So whether the two nodes should be linked or not based on the probability. So these are two different mechanisms of the differentiable graph module, and they also have like a different inference steps. So now let's go to the first work. It's called F3, federated feature fusion. So let's consider this kind of learning scenario. It's called vertical federated learning. It's a little bit different from the general federated learning because for general federated learning, we generally just have the different samples in different clients. But for vertical federated learning, it's split by the features, not by the samples. So assume that you have different data owners, and if each data owner will just have some different forms of the observations for the same phenomena of interest. For example, if you have some multivariate time series data, each owner may have only one time series variable in the time series data, or maybe just a subset of time series data. And then the data owners train their own local models in isolation, so they don't have any communication with each other. And also to save the communication cost, you can have a local model pre-trained at each local station, and then a global model to do the aggregation. So that's a vertical federated learning setting. So a typical example is power grids. Assume that you have some power grid network, and in each local station, you have a data owner, which can have the PMU data. You have the phasor measurement units, and then they don't share the data, and they can just train their local model independently. And at the end, because you want to aggregate all the information for the local stations for the whole power grid network, so you need to have a global model to do the aggregation. So this is a typical data structure. So this is the power grid data. So we have different local stations, and in each local station we have different sampling frequency. We have different variables of the PMUs, and we have like sometimes we have missing data, and we have some anomaly events. And the final task is just to predict, okay, in the future window, whether there will be an anomaly event or not. So you can imagine if you just use the local data, somehow the information is not complete. So you have to consider also all the other stations. So you have to consider the global model to aggregate all the information of the local stations. And this is the learning objectives. So you have the local part and the global part. The local part is just used to learn the representation. So you have a fan function, generally it's a neural network, to learn the embeddings of your time series. And then you do the aggregation. So here I don't assume what kind of model you use for aggregation, but it's just some global model to do the aggregation. And then at the end, you just predict the anomaly event in the future. So to save the communication cost, generally the local and global model training is separated. That means you can have a two-step training. First, you train the local model independently, and then you train the global model separately. So there are some challenges here. So assume that each local model is just trained independently because they don't have any communication. They don't have any information from other local stations. So if you have a model, actually the output of the dimensions are actually not aligned. For example, if you want to do GNN, because the features are not aligned, you can actually, not do the aggregation very well because your features are actually have different meanings. So you have to have some alignment mechanism to align the different dimensions to have the same meaning for each dimension. And then the next challenge is that because it's a power grid network, so that means your local stations will have some latent interaction with each other. So you have to consider how they communicate in the latent graph. So you assume there is a latent graph, but you don't know. You need to learn it. OK, so how do we do that? This is the federated feature fusion framework. So first, we do the latent representation training for each local station. And then we use the synchron-based feature alignment to do the feature alignment before the aggregation. And at the second step, we just assume there is a latent graph, and we can just do GNN to do the aggregation. But then how do we learn the latent graph? OK, the first step, we need to learn the alignment. So we just assume that for each local station, before they send the message to the global model, we will have an alignment matrix to project their representation to the local model to make them align with each other. So we will have a parameter, which is just a permutation matrix. And this permutation matrix can be, can be adjusted doubly stochastic matrix, or it can be even without any constraints. But here we just use a synchron knob algorithm to generate the doubly stochastic matrix. That means the sum of each row and the sum of each column is just 1, so it makes it a permutation matrix. And you can just assume any initial matrix, and then you can just use synchron knob to make it a permutation matrix. So that's quite simple. And then when we come to learning the latent graph, so we design a new mechanism using this inverse CDF. So actually, there are many methods to learn the latent graph. So the most common one is to use Gamble softmax. So you can just assume, OK, you have some latent probability, and then you can use Gamble softmax to sample the discrete graph. But here we design a new mechanism. It's called ICDF. So assume that we have any arbitrary CDF function, f theta, and theta is a bias. So using this kind of mechanism, we can just use it to approximate the Bernoulli distribution. So that means we can use this kind of z to approximate the samples of Bernoulli distribution with the bias theta. So we have some theorem to demonstrate that it's equal to the Bernoulli distribution at the end, but here I will not show it. OK, so at the end, we just compare many different algorithms, like the traditional vertical federated learning. And also we compare with some algorithms using transformers. And we compared with the algorithm without any graph, just to do concatenation. So it's quite interesting. So if we use transformer, essentially it's also learning some kind of similarity-based graph, but it doesn't perform so well. But using our method, it's much better. And also the alignment here so makes the learning much better than without any alignment. So that's the result. OK, so the second work is quite old, but I think it's also a typical work about how to learn the correlation graph. So the context here is about predicting the unknown drug-drug interactions. So assume that we have one drug. Generally, the patient takes one drug, it's OK. But when the patient takes a lot of drugs, some drugs may have interactions with each other, and it will cause some adverse reactions. So we don't want to have this kind of drug-drug interaction, which causes the adverse reactions. So we have to predict, OK, possibly there are some unknown drug-drug interactions, and we can just use the existing DDS to predict the unknown ones. And actually, if you do the link prediction task, you will see in the OGB benchmark, there is a data set called OGBL DDI. That's a quite popular link prediction task. So in the drug-drug interaction prediction tasks, actually, for the drug-drug interaction types, there are many correlations. For example, this is a little bit complex, but you can see we have a center node, which indicates one drug. It's called warfarin. And when you take this drug with some other drugs, it will cause two different adverse reactions, inhibit clotting and intestinal bleeding, and these adverse reactions always occur, not always, but often occur together. And when you take another drug like I don't know how to spell it, but when you take other drugs, generally you will have another kinds of adverse reactions. But these kind of different adverse reactions will also have some correlation with this kind of inhibited clotting and the gastrointestinal bleeding. So that means your DDI interactions, they will always have some correlations with each other. So you have to consider this, because when you take this drug, warfarin, generally this kind of adverse reactions will come together in some way. Okay, so how do we learn the latent graph? How do we learn the latent correlations? So in about 2016, there's a typical work called SPANS, Structured Prediction Energy Networks. So it's based on the energy-based model. So generally, they just assume, okay, there is an energy function, and I just need to minimize this energy function. And by decomposing this energy function into the energy between X and Y, and also between the Y itself, then we can consider the higher order interactions between the different Y's. So you can say in the local component, we only have the interaction between the feature of X and the label Y, and in the global energy function, we have the interaction of Y's. So it can be linear, or it can be bilinear, or even higher order. For example, if you are familiar with conditional random fields, actually the linear chain conditional random fields can be written in this kind of form. So it's a global energy of the CRF. It's just like the bilinear function of Y and the linear function of Y, and they are summing up together. So generally, they just assume that there is a fully connected interaction graph in the labels, and you just need to consider all the pairwise interactions in your energy function. But of course, there are some variances, so you can also induce some sparsity in the interaction graph, but that's not our scope. So in our work, we consider that the DDI types, they may have some correlation graphs, but it's a little bit different. So how is it different? So sometimes in the DDI graph, it's not only about the interaction between labels and labels, but also it's conditional independent. It's conditional dependence. So the label So the labels of DDIs, they are not just interacting with each other, but they are also interacting with the drug nodes. So it's drug dependent. So instead of considering PY, Y1, Y2, you also need to consider PY1, Y2 giving X. So you need to consider what's the impact of this node. So in that sense, we cannot decompose the energy function into the local part and the global part, because the local part, they don't consider any, label interactions. But the global part, they don't consider any X. So it's only about Y. So how do we do that? We just assume that we can use a graphing network to, model all the interactions between all the Y's and all the X. So that's quite simple. Assume that you have a center node X, and all your Y label is just the edge types connecting to this center node X. So then, based on the message parsing, you are actually receiving all the messages from this Y and X. Then you can use graphing network to aggregate all the information to get your energy function. So that's a graphing network-based energy function. And then we just need to minimize this graph energy function to get the final label. So we also use the span method to do the inference and training. So for the inference, you just need to do the minimization of your energy function. And for training, it's a little bit different. So you need to use the structured hinge laws to get your training network. So your training network and your inference network actually are a little bit different. So they use a technique called cost-augmented inference network to do the training. So they just use another neural network to approximate the prediction YL in the training phase. And then after doing the training, they got all the parameters of this cost-augmented inference network, and then they put this parameter in your final inference network, and then you can minimize the energy function in the inference phase to get your final label. So that's a two-step of spans. And we did a minor revision, so we just combine these two types together, so we do a joint optimization for both training and inference. And these are the final results. Of course, the data prediction result is quite good compared to the baselines. And we also analyze the correlation of our model and the ground truth. So the higher bar means the higher correlation between the ground truth and the models. So you can see our model and the variant of our model can always beat others. So that means the correlation analyzed by our model can be quite close to the ground truth. The final one is called graph CBM. It's an ongoing work. So it's about interpretability in the CBM, the concept of bottleneck models. So this is the background. Concept of bottleneck models is recently a very popular interpretability method for deep neural networks. So the basic idea is that, for example, if you want to do an image classification task, generally you are just giving an image and use a black box neural network to do the final label prediction, but you cannot get any explanation. You don't know why you get this kind of prediction. But CBM, they just add another intermediate layer. So instead of predicting the final label, they first find some concepts associated with the final label. For example, if you want to predict whether an image is a bird or not, so you can first find some concepts related to the label bird. For example, maybe the color, the wing, the legs. So you can first predict the concept scores. So you know whether the image has this kind of concepts. And then based on the concept predicting score, you can predict the final label. So the concepts are actually regarded as a bottleneck layer. That's why it's called concept bottleneck models. And once you have the concept predicting score, you can explain why you get this kind of labels because your image has this kind of concepts. You can also do some intervention. For example, if you do the medical image analysis, you can ask some clinicians to correct your prediction of your concept label, so your final label will also be correct. So that's how you can do the intervention with the concept bottleneck models. So one problem of concept bottleneck model is that here they assume all the concepts are just independent. But in practice, you can imagine not all the concepts are independent. For example, in the previous example of the labels, so if you have a beach, generally it's associated with ocean or sand. So similarly, for concepts, they are also have this kind of correlation. For example, if you have the black color for the for the wing, maybe you also have the black color for the body. So you can imagine some correlations among the concepts, but in previous concept bottleneck models, they never consider that. So what's the problem? So if you don't consider this kind of correlation, when you do the intervention, you can imagine if you just do the intervention for one concept, it doesn't impact others. It only impacts the final label. But that's not true because your concepts will have some correlation with other concepts. So actually, when you do the intervention for one concept, it should impact some concepts correlated with this concept, right? So that means you need to assume there is a latent graph which can connect all the concepts. So when you do the intervention for one center concept, these concepts should also change the scores of the surrounding concepts. So then, we need to learn the latent graph of the concepts. Okay, and here we have some assumptions. First, the latent concept graph should be label agnostic. That means when you change the label, the concept graph shouldn't be changed. So it should be self-supervised instead of supervised. And then the graph should be unified for all the pictures. It should be changed dynamically. So we just assume there is a unified concept graph which is not changed according to different pictures. But the different picture can activate different nodes in the unified graph. That means each picture will correspond to one activated subgraph in your unified concept graph. And then the semantic meaning of the activated concept subgraph should be consistent with the original image. So if you use some encoder to encode your image, and then you use a graph encoder to encode your concept graph, so they should have the similar encodings. And then we can use contrastive learning, right? Because you want to have different views of the image. You have the image encoder, you have the concept graph encoder. Then you should have the similar meanings based on different views. So this is the graph CBM architecture. First, we use some we use some image encoders and text encoders to get the similarity between the image and text, so we know which concept should be activated in the candidate concept set. And then we assume that there is a latent graph, so this latent graph will be just a learnable parameter. And then you activate a submatrix of this latent graph. And then you do the GNN message parsing to update your concept embeddings and also the concept scores. So based on your new concept embeddings, you can learn the graph embedding of your concept graph, and also you can compare it with your original image encoding. So they should be consistent with each other. You can do the contrastive learning. Then you can learn all your parameters, your latent graph parameter, your encoders. And this is the image classification results. So we compare with some label-free CBM and the PCBM. So generally with the latent graph, it can perform much better. And especially when we do the intervention, so that means we use the correct concepts to correct the wrong concept predictions. You can imagine with the latent graph, the intervention of the concept will have like a bigger impact. So that means generally an intervention will cause like a more correct final label predictions. And this is an example of the latent concept graph that we learned from the medical image. So it's about the chest expert data set. So you can say, actually using different backbones, the CPM and CEM, our methods can learn like a very similar correlation graphs among the concepts. And this is the conclusion. So not only about our works, but also a summary of some previous conclusions about graph structure learning. So actually from these two benchmark papers, they have very interesting conclusions about graph structure learning. So in the OpenGSL, they have a very interesting conclusion. So higher homophily in the learning structure, that means if you just use the KN graph to learn the similarity between the nodes, it doesn't always perform very well. So that means the homophily in your learn structure doesn't always increase your performance. Higher homophily doesn't mean higher performance. And in the GSLB benchmark paper, they also have interesting conclusions. So the graph structure learning is generally very helpful in node classification tasks, but when it comes to the graph level classification tasks, it's not so useful. Sometimes it's useful. It depends on the data. And also, the learning graphs are actually very robust and generalizable, so it doesn't, it's not impacted by your backbone GNNs. So if you learn the latent graph structure, it's generally useful for all kinds of GNNs. But they also have their own issues. So generally, learning the graph is very computationally inefficient. So you need to maybe make it more sparse or make it more learning efficient. And summary of our works. So we have talked about 3 different works: the latent graph of time series, the latent graph about the labels, and the latent graph about the concepts. So yeah, that's all. Thank you.
So I have a question for the second part, the drug-drug interaction prediction. Okay. You have several edges in that layer that you have between drug-drug. Have you ever considered extending the algorithm to heterogeneous network, like adding a disease layer that
I see.
A drug node would have a relationship with a specific disease, either it treats or causes the disease, and you predict the edge type between drug-disease interaction? Which hasn't been done before because it's signed graph.
Yeah, I think that's an easy extension. Yeah, so it should work. Yeah, it should work because you can still use the graph neural network. It's just like you change the graph neural network backbone into the heterogeneous graph neural network, right? But we need to check. Yeah.
Thank you.